All right, so let's get to the review. It's gonna go kind of quick, but we can get through it. All right, so when we're evaluating, the idea is that we want to set the log equal to a variable. It doesn't matter the variable, x, y, z, a, b, because at the end of the day, right, this is just a number, and we got to figure out what does this number equal, and let's set it equal to a variable, then convert it to an exponential. So set equal to a variable, then convert to exponential. Those are our goals. All right, so this is equal to x. So the way we convert the base raised to this equals this. So 6 raised to something equals 36. So sometimes these are going to be pretty obvious, right? I say obvious, like 6 to what power equals 36? Well, we know that 6 squared is 36. But let's say that wasn't obvious, right? Then what you'd want to do, if it wasn't obvious, is you want to somehow make them have the same base. So make have same bases, meaning somehow turn 36 into base 6. Right, so they both have the same base. And here, when they have the same bases, then you can set the exponents equal to each other. In this case, x would be equal to 2. So that means that this log base 6 or log base 6, 36 is equivalent to 2. In this case, x is equal to 2. All right, number 2. 16 raised to this equals this. So 16 to the x power, to what power, equals 1/4. I think if we bring the 4 up, right, 4 to the negative 1 power, that's the same thing as 1/4. And then make them have the same base. So this would be 16 is really 4 squared. So 4 squared to the x power. Right, that looks kind of confusing. So what I'm doing is I'm rewriting 16 as 4 squared, but that is still to the x power. And right hand side, 4 to the negative 1. So when you have a power raised to a power, you multiply. So this means 2 times x is 2x. All right, so in a sense, we don't care about the bases any longer because they match, right? So we're just going to set the exponents equal to each other. So 2x is equal to negative 1. Solving for x, we see that x is equal to negative 1/2. So negative 1/2. Now, could you have saw that? Like, the question is, can you see that from the beginning, given 16 to the x power? Some people can. I'm going to assume that you don't see it. So, show you how to work through it. All right. Number 3. So 64 to what power is equal to 4? So the number's getting smaller. It's kind of a hint. So 64 to what power equals 4? Again, I can write them as the same base. So 4 to the 4th power, right? 4 times 4 is 16 times 4. Oh no, 3rd power. It's implied that there's a 1 there. So this is going to be 3x is equal to 4 to the 1st power. And again, we make the exponents equal to each other because they have the same bases. Like if the bases didn't match, we can't do this. So 3x is equal to 1. Therefore, x is equal to 1/3. Okay. Number 4. 2 to what power is equal to 132? 1 over 32. All right, so the 32 can come up, so the exponent is going to be negative. So 2 to the what power is 32? 2 times 2 is 8. No, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 5. So x is equal to negative 5. Oh, it's a nice property. When the base and the argument match, it's 1. It's 1. Let's say you don't remember that. Then that means that 7 raised to what power is 7? The bases already match, so x is equal to 1. So the property tells us that when the base and the argument match, the answer is 1. Even better, when the argument is 1, this is equal to 0. So the log of anything, base anything of 1 is going to be 0. Again, let's pretend you didn't know that. So this would mean that this is equal to something, right? X. So 5 to what power is 1? And that, and here we see that exponent rules, right? Anything to the 0 power is going to equal 1. So x has to be 0. It can only be 0. All right, calculator. I don't care about that. All right, expanding. So there's 3 main rules. Division goes with subtraction. They go hand in hand. Multiplication goes with addition. And then we know that the power can come down. So these are the three properties. All right, so number 9. Natural log of x minus or x over y squared. First thing I'm going to do is apply the power to what's in the argument. Now, yeah, I could bring the power down, but I think, it's all technique. I want to apply the power first. That's just my personal thing. So natural log of x squared, y squared. Okay, because this is division, right? That to me is subtraction, right? It looks like a subtraction sign. So this is going to be natural log x squared minus natural log y squared. Right? So you got to associate division and subtraction. Then last, the power comes down in front as the coefficient. So final answer, 2 natural log x minus 2 natural log y. So you could have brought the power down first, but then you would have to remember that that 2 would have to distribute to everything. So either way, I personally like to do it first, so that way I don't forget. Okay, this is multiplication, right? All of these are being multiplied. 9 times a times b to the 5th. So this is, and then the base is 10, right? Nothing's written, so we understand that it's 10. So this is going to be log 9 plus log a plus log b to the 5th. And then the power can come down. Okay. So remember, I guess one way to think about this is that, right, the argument, the part that's in the parentheses, when that's being multiplied, then you can open this up essentially. You can expand, and then each term gets the log. Vice versa, right? Like, which is coming up here in a second. Notice how you have 3 different logs being added together. So that means the arguments come back together in multiplication. So it's going to go both directions. Our number 11. These are all being multiplied. The only difference is we have a cube root. So I'm going to rewrite the cube root first, right? Because that can be rewritten as an exponent of 1/3. So this is going to be log base 6 of 7 a b squared, and all of this is to the 1/3 power. Now I'm going to apply the 1/3 to each the a and the b squared, right? The 1/3 never sees the 7. It's only applied to the a and the b squared. So this is going to be, right, this is still the rewrite step. We haven't actually started anything yet. So 7 a to the 1/3 power, b. So power raised to a power, you multiply. So 2/3. Now, because they're each being multiplied, then I can break this up with addition. So each of these terms, the 7, the a to the 1/3, and the b to the 2/3, are going to each get a log base 6. Not only that, the powers are going to come down. So I can do it all in one step. Like, once you get nice, you can do the power rule at the same time you break them up. So watch. It's going to look like this. Log base 6 of 7 plus log base 6 a to the 1/3, that's going to come down, plus log base 6 b to the 2/3, that's going to come down. So there it is. Don't get your b's and 6's mixed up. Okay, number 12. Know that the parentheses are implied, right? It's implied. So natural log of all of this. So we have a couple compound things happening. We can do it step by step. So I think the division part is what I would do first. So this means natural log of x cubed minus natural log y squared times z. Okay, so the minus, right, this is going to be the negative or the minus. It's applied to everything in the brackets. Brackets and parentheses are synonymous. They're the same thing. So this part here is multiplication. So this is going to be natural log y squared plus natural log z. So because the negative has to distribute to everything that's inside, this is going to be, so the power is going to come down here. So this is going to be 3 natural log x, right? Because the power can come down front, minus 2 natural log y. Again, the power can come down in front. And then minus natural log z, right? That this negative has to distribute to everything that's inside. And it just so happens there's two things inside, right? Natural log y squared plus natural log z. So the negative hits both of those. Okay, so here we have, now we're condensing. So it's expanded and we got to put them back together. So here, all the bases match, log base 9. And we have addition. So that means the arguments are going to be multiplied. So the arguments are 11, A, and B. So these are going to be multiplied with log base 9. So log base 9, 11, A, B. Right, they're all being multiplied. Okay. Number 14. All right. It's subtraction, so that means division. And always be on the lookout for coefficients, right? Coefficients in front of logs can move up to become powers. So this is going to be log base 3, right? Because it's one big log. There's two logs, and they're coming together as one. So it's going to be u cubed, right? It can come up, divided by v. So anything else I want to say about this? Just remember that when you're subtracting, right, when logs are being subtracted, the farthest right, like whatever's to the right, that swings down underneath. Right? This is to the right, so it's going underneath the u, right? Like the way that these expand and condense, it goes underneath. All right, 15. So this can look very intimidating because of the fractions, but understand that the natural log x and natural log y, that's a number, right? That's a figure that's being divided by 2. So it's not like the divided by 2 isn't part of the argument. Like, for instance, in number 12, right? This was the natural log of something that has a fraction in it, a top and a bottom, the natural log of that thing. Here, this is completely different. This is not the same thing at all. This is the natural log of something, x, and we're cutting it in half. We're multiplying it by 2. So that means this, right? It has a coefficient of 1/2. So that's what this means. Both of these do, actually. So with that being said, here I feel like it's clear that the coefficients will come up. So it'd be x to the 1/2 power, y to the 1/2 power. But the 1/2 power is basically a square root. So watch. So these will all come together. 7 x to the 1/2, y to the 1/2. You can probably already see where this is going. So this is going to be natural log of 7 xy to the 1/2. And now the 1/2 is just square root. So this is actually sufficient in my opinion. This is condensed. Some people might prefer this, which, it all depends on what's simpler or what they define as simple. I like seeing either or. It's whatever. Okay, we have some compound stuff happening. There's 3 things. We have addition and we have subtraction. I think it's best to work left to right. So if we combine these first, the first 2 terms, and then the negative part or the division part second. So this is going to be so let's do the exponent parts first, and then log x to the 5th times 9. I can put the 9 in front. All right, it's multiplication. It doesn't truly matter which way it goes. And then log minus log y cubed. All right, so this is going to come together. Again, it's subtraction, so division, right? So this is going to be log, again, base 10 because there's nothing written. In the numerator, 9x to the 5th over y cubed. All right, finding the inverse of each function. So the steps are going to be switch x and y. And then solve for y. Usually when you solve for y, this is going to take converting logs to exponential form. And sometimes making the bases match. So then you can set the exponents equal to each other. So let's see. All right. So x and y are switched. And now we start solving for y. We're getting the log by itself. Okay, so we've gotten the log by itself. We want to get to the y. There is a hardcore rookie mistake that everyone makes in the beginning. So you cannot divide both sides by just ln. Like, it may look like it, but that doesn't even make sense, because ln itself is not a number, right? Ln is a function, meaning like f of x, right? F of x, this is the notation that we use to denote a function, right? This isn't f times x, right? This is f of x. So the same idea applies with the logarithm notation. Ln, it's just notation. So you can't divide by ln. That's what I'm saying here. So there's got to be some way to unlock the logarithm. And there are a couple different ways, depending on who your teacher is or the techniques that you're taught. The most basic way is that natural log is actually log base e. All right, so a little note is that natural log of x means log base e of x. So what I'm saying is x plus 3 is equal to log base e of y minus 8. So y minus 8 is the argument. So now when we convert this to exponential form, log base e raised to all of this equals all of that. So base e, the exponent is x plus 3, and this is equal to y minus 8. So notice the log has been unlocked, right? It's gone away. So we can get to the y. We isolate y. So I'm just going to add 8 to both sides. Now the second rookie mistake is when you add 8 to both sides. For some reason you think, oh, I'm going to add it to the exponent, right? E to the x plus 3 plus 8. That's not true. X plus 3 is up in the exponent, right? Think of it as like x squared. Well, if I'm adding 8 to both sides, I'm not adding it to the exponent. I'm adding it just in general. So this is going to be e x plus 3 plus 8 equals y. And this is the inverse. All right, so it is worth mentioning, right? Because again, I said it's all about how you're taught and techniques. So one technique is that when you have natural log, specifically natural log, and it's by itself like it is in the top left corner of the screen. So one idea is that, well, the idea in algebra is that I can do anything I want to an equation as long as I do it to both sides of the equation. So, in a sense, we can raise both sides of the equation, right? Like I'm applying e to both sides of the equation, right? This is base e to the power x plus 3. On the right-hand side, we have base e to the power ln y minus 8. And what happens, in a sense, is that the e and the ln, anytime e and ln meet up, they cancel each other out. And this is mainly because they're inverses of each other. So when natural log ln and e meet up, meaning e to the ln or ln e, right, ln e, they always undo each other, right? They cancel each other out. And that's exactly what we have here. So if you kind of compare what's on the left and then what's in the black box on the right, e to the x plus 3 power, and then that'll all be equal to y minus 8. When the e and the ln cancel, the exponent y plus y minus 8, that basically comes down, and that becomes the bottom number, like not in the exponent. It's no longer an exponent. It's just what it is on the right hand side. So that's one way to think about it. All right, 18. Y equals log base 10, right? Log 2x minus 5. Okay. Swapping the x and y. So here, it's understood, right, that it's base 10. So then we can rewrite this as base 10 raised to x equals this. So 10 raised to the x, so some power, equals 2y minus 5. And now we just isolate y. Plus 5, both sides. So 10 to the x plus 5 equals 2y. Divide both sides by 2 because we want to isolate the y. And we see that y is equal to 10x plus 5, all divided by 2. So I guess we could box that. Okay, 19. X is equal to 6 to the y minus 2. All right, swapping x and y. I'm going to add 2 to both sides. So x plus 2. So notice here we didn't have to convert just yet. Is equal to 6y. Okay. So the variable y that we're solving for on the right-hand side is as isolated as it can get, right? Like it's 6 to the y. So when the variable is in the exponent, there's only one tool that we have that brings the exponent down, and it's a log property. So again, the rule, golden rule, right? I can do anything I want as long as I do it to both sides. So what I'm doing is I'm taking the natural log of both sides. When I do that, that allows the variable to come down because that's a property of the natural logs or of logs in general. So log x plus 2 is equal to y natural log 6. Okay, here, the way we isolate y is we have to divide both sides by ln 6. Now, this is a natural spot for some people to be confused and be like, bro, you just said we can't divide by natural log. So if you rewind and see what I actually said, like you can't divide by just the ln part, right? Ln 6 is a number, right? It's an irrational number, but think of it like a number, like 2. It's just a number. So this is y times a number. And the way you isolate y, you have to divide by that number. So on the right-hand side, they cancel. And basically our final answer is y equals ln of x plus 2, right? This is a number, over ln 6, which is another number, right? 2 completely different logs, right? You can't combine these using like our condensing methods, right? This isn't, they're 2 separate logs being divided. There's no property that combines them. Okay. Okay. Y equals 10 to the x, all divided by 4. So step 1, x is equal to 10 to the y divided by 4. Okay, we're going to isolate the y, or the thing that has the y in it. So I got to multiply both sides by 4. Therefore, 4x is equal to 10 y exponent. Again, the y is in the exponent. So I'm going to apply the natural log to both sides of the equation, which is going to allow the y to come down in front, giving us natural log of 4x is equal to y natural log of 10. Right? And this is being multiplied. So to isolate the y, we have to divide both sides by ln 10. So we get y is equal to the natural log of 4x divided by the natural log of 10. Again, you cannot simplify the 4 and the 10 because they're both even, right? That 4x is contained inside of a natural log, just like the 10 is contained inside of a natural log, and therefore they can't see each other. All right. Swapping number 21. Swapping x and y. All right, we're solving for y. So I got to get rid of all the extra things, right? So I can divide both sides by 5. So we get x over 5 is equal to log base 4 y plus 2. The log's all by itself, so we have to get to the y. So this means 4 raised to this equals this. So we convert it to exponential form. And the last step, subtract 2 from both sides. So we get 4 x to the 5th minus 2 is equal to y. Okay. Switching x and y. I'm going to add 3 to both sides. So x plus 3, y plus 5. Okay, we've isolated y as much as we can. So that means the y is in the exponent. And when the y is in the exponent, the variable is in the exponent. The only tool that we have to bring the variable down, right? Anytime you need to bring the variable down, that should be like second nature. I need to bring the variable down. Oh man, I need to use a natural log. So I'm going to apply the natural log to both sides. So on the left-hand side, natural log x plus 3. And on the right-hand side, anytime ln and e match up, right? Anytime they see each other or they touch or however you want to think about it, they basically go away and the exponent is what it is. And then to isolate y for the final step, right, we subtract 5 from both sides. So final answer, ln x plus 3 minus 5 is equal to y. Okay. All right. We're almost done. Solve each equation. So here, we're going to be solving for the variable x, y, whatever, in a, whatever the variable is, that's what we're solving for. And we can use any and all of the rules or properties. Really the key is that when you get them both in either both exponential forms, you want the bases to match. Because when the bases match, we can let the exponents equal each other. Or you want logs on both sides, and you make the arguments equal to each other. If you have a log, and just another log, which you'll see here in a second. All right. So I'm going to start working this thing. On the left-hand side, this negative x, I can rewrite this as 81 to the x, right? If you make it positive, it brings the denominator up. And this is equal to 27 negative x plus 2 in the exponent. All right, so my first thought is that 81 and 27 are both divisible by 3. Or multiples of 3. Some might say 9. Okay, cool. Yeah, I agree. They're divisible by 9. But you can't write 9 with an exponent to make 27. Not right away. So 9 squared is 81, but 9 to what power gives you 27, right? Like that's not obvious. So 3 is the next best thing, right? So 3 to what power is 81? 3 times 3 is 9, times 3, 27 times 3 is 81. So 4 to the x power, so you multiply, is equal to, so 3 cubed, right? 3 times 3 is 9, times 3 is 27. So 3 cubed, and that's being raised to negative x plus 2. So again, you have a power raised to a power. You multiply. This is going to have to distribute in a sense. Because the bases match, I no longer care about the bases, right? I'm making the exponents equate to one another. So this is going to be 4x equals negative 3 plus 6. Negative 3x plus 6. Right, because the 3 has to distribute. So this is just an algebra 1, basic one variable algebra. Haha. So this is going to be x is equal to 6/7. Okay. Okay. 64 can be rewritten as 4 to the 4 times 4 is 16 times 4, 64. So cubed. So the bases match. That's good. So now the exponents, after we multiply here, right? 3 times 3 is 9. So this is going to be 3n minus 1, 9n. All right, negative 1 is equal to 6n. So n is equal to negative 1/6. Okay, logs base 5 of negative 2v minus 4 is equal to log base 5 of 12. So here, this is ideal. The log base 5, right, because these parts match, right, log base whatever, like, that's ideal, right? There's nothing else we have to do. Like, I really don't care about these anymore. Because if I have a log, both logs on both sides of the equation that have the same base, then their arguments must match. So this is basically negative 2v minus 4 is equal to 12, right? The arguments have to match. Basic algebra. Solving for one variable and then dividing both sides by the coefficient. So v is equal to negative 8. Okay, this is not the same problem. So here we're going to have to, so we have two logs, but they're on the same side of the equal sign. And they're being added. So that means that the arguments of each of the logs can be multiplied. Right, the underlying parts can be multiplied. So we're condensing this down into one log. So log base 2 of 3 times x plus 1. And this is equal to 4. Now, do we have to distribute? You don't have to. It's kind of irrelevant because, think about it. We're solving for x. So x is already by itself in a sense, right? There's no coefficient. So I'm going to say 2 raised to 4 equals all of this. So 2 raised to the 4th power equals 3 times x plus 1. So do you see why distributing the 3 would be irrelevant? Because then you'd have to divide by 3 at some other point. So here I'm going to, I guess we could simplify 2 to the 4th power. 2 times 2 is 4, times 2 is 8, times 2 is 16. So 16 is equal to 3 times x plus 1. Divide both sides by 3. So 16 thirds is equal to x plus 1 minus 1 minus 1. This is, so 16 over 3 minus 1. You could actually combine the left-hand side, right? Like 1 is really 3 over 3, right? We have to get a common denominator. So 16 minus 3, 13. 13 thirds. Okay. All right, I'm going to do the next 4. All right, same idea. The 2 logs on the left can be combined because it's subtraction. We can combine them using division, right? Subtraction, division. So this is going to mean log base 8 x plus 3 over x is equal to 1. So now that we have 1 log, we can convert it to exponential form. 8 raised to the 1st power equals all this. 8 to the 1st power, which is just 8, should equal x plus 3 over x. Okay, solving for x, right? We need to get x by itself. Multiply both sides by x. So 8x is equal to, the x's cancel on the right, x plus 3. Subtract x. So 7x is equal to 3. Divide both sides by 7. X is equal to 3/7. All right. It's slightly harder, but doable. So again, addition. So that means they're going to be multiplied, the argument, that is. So log base 9 x times x plus 24 is equal to 2. So base 9 raised to 2, so squared, equals all of this. So 9 squared, basically. 9 squared is 81. And this is going to equal x times x plus 24. Okay, here, since we got to get x by itself, we have to distribute. There's no way around this one. So when you distribute, 81 is equal to x squared plus 24x. Okay, x squared, I mean, this has got to scream quadratic, right? Like, there's no way around, like, it has to be a quadratic. So if we want to solve for x, when there's an x squared, we put everything on the same side. And this is going to be equal to 0. So this is factor or quadratic formula. Can it be factored? Multiples of 81 that add up to 24. 27 and 3. Right, 27 times 3. 246 plus 2. Yeah. So this means, but we had to add them up. So it's negative, right? So one of these has to be negative. So 27 and 3. One of them needs to be negative. So we look at the sign here. So that means a smaller one, right? Because negative 27 times negative 3 is negative 81, obviously. But then 27 minus 3 is positive 24. So that's that. All right, this is equal to 0. So that means each of these are going to be equal to 0. So we can just flip. We can flip the signs. All right, so we have two answers. But oh, you can't see it. So we have two answers, and we have to consider. Right, if it's just one answer, then we're good. But we don't have just one answer. We have two answers. So we have to see, are these answers legit? And the way you do that is you plug in to see if these would actually work. So if I plug in negative 27, right? Negative 27. Well, logs, we know, can't have a negative argument. Like the part inside the log cannot be negative. The input can't be negative. So right away, this one is garbage. X equals 3. So we can plug in 3. Okay, that'll work. And then 3 plus 24, positive number, will also work. So 3 is legit. Okay, we have addition, 2 logs. So again, multiplication. So this looks very much like the last problem. So it's going to be very similar with the whole factoring part. So log, no base, so base 10, x plus 48 equals 2. So, right, there's a 10 here. That means, so 10 raised to this equals this. So 10 squared, which is 100, equals x plus 48. That's an 8. Okay. Right hand side, distribute x squared plus 48x. Okay, we have to subtract 100. This is equal to 0. All right, so two numbers that make 100 add up to 100. No, two numbers that multiply to make 100 that add up to 48. So 50 and 2. So 50 times 2 is definitely 100. One has to be negative because the middle term is positive. The smaller one is negative, just like in the last scenario. Right, so if we check ourselves, 50 times negative 2 is negative 100. 50 minus 2 is negative 48. 50 minus 2 is positive 48. And this is equal to 0. So this means that x is equal to negative 50 and x is equal to positive 2. So again, we look and see that the negative one is no good. All right, here's the last problem I'm going to do. Right, I get it. There's graphing. We can you can look back at the graphing videos. Okay. Subtraction, that means division. Log base 2 of 5x squared over 10 equals 1. Going to rewrite this in exponential form. 2 raised to this equals this. So 2 to the first power is just 2 equals 5x squared over 10. If we multiply both sides by 10, right, because we're isolating x, on the left, 10 times 2 is 20. And this is equal to 5x squared. All right. Divide both sides by 5. 20 divided by 5 is 4. Oh, that's nice. Because look, 4 is equal to x squared. When we solve for x is equal to, right, anytime we introduce the square root, we have to use plus or minus. Square root of 4 is 2. Right, the square root wasn't there. I'm using the square root to undo something. So anytime that I introduce the square root to do the thing that I'm doing, you have to do plus or minus. So that means x is either positive 2 or x is either negative 2. So when we look and we see, okay, will this work? And actually both of these will work because right here in blue, the x, right, that part's mean squared. Now I get it. I said that the arguments can't have a negative number, which is true all day. But the argument is 5 times x squared, right? It's a like a package deal basically. So the x could be 2 or negative 2 because when you square negative 2, you still get positive. So no matter what, this is going to be this is going to come out to a positive number basically. All right. I'm not concerned with the last two. All right, good luck.